Okay. Now, yesterday we spent a lot of time talking about domain. A lot of time. So you should, hopefully, if you were listening yesterday and keeping up, you should be able to look at this and say, Mrs. Ford, we're going to have a problem if x equals -2. Everybody see that? X cannot equal -2. That means, graphically, at -2, x equals -2, there is a vertical asymptote. So we're going to have a vertical asymptote at x equals -2 because in this problem, x can't be -2. And cannot be's are graphed as vertical asymptotes. Now, do you remember yesterday we talked about removable discontinuities? Do you remember that? And what did we say about removable discontinuities? How did they come into the problem, Lane?
If they can be canceled out.
Exactly. Now, when I look at this problem, is there anything that's going to cancel out of that problem? And can I factor and cancel in this problem? No. So this problem won't have any holes. There'll be no holes in this problem. Because the only way you get a hole, which is kind of the unmathematical term for removable discontinuity, the only way you can get a hole is if you can cancel. This problem, I can't do that. Now, horizontal asymptotes. We haven't talked about this. We kind of saw them on our calculators yesterday, but we haven't talked about it, and we need to. The horizontal asymptote in this picture is at y equals 2/5. Now, horizontal, y equals 2/5. I'd like you to look at the problem, and do you have any idea, just a wild guess, where that 2/5 might have come from?
Coefficient of each x.
And do you have any idea why that is, Andrew? You're right, you are exactly right. This is where the 2/5 came from, absolutely. But do you have any idea why that is?
I don't remember from last year.
I don't know if you guys talked about this last year. Maybe you did. Did you talk about it last year?
I remember it being more like horizontal, like when it was like x equals instead.
Oh, okay. The reason you have a horizontal asymptote at 2/5 is this. The horizontal asymptote is that's what the curve approaches. When I sketch this, when I'm finally done sketching this, it is going to have a shape maybe like this. Okay? The curve is going to approach that asymptote as it heads off the page. Now, that means that as x gets really, really, really big, the function will approach 2/5. Now, what does that mean? As x gets really, really, really big, the value of this function will approach 2/5. And here's why. If you think about x being a number like 1,000,000, what would your numerator be approximately if x were 1,000,000? Approximately. 2 million? What would your denominator be approximately? 5 million? And what do you get when you put 2 million over 5 million? You get 2/5. So your horizontal asymptote describes what happens to the fraction when x gets really, really big. When x gets really, really big, these don't even matter. If you're talking millions and billions, 3 and 10 don't even matter. So you have 2x over 5x, which reduces to 2/5. Now, intercepts. We know what those are. Intercepts are the places where the curve crosses the x-axis or the y-axis, crosses n-axis. To find intercepts, anybody know how to do that? I know, you may not remember. Well, if we are crossing an axis what can you tell me about one of these points? If I'm on the y-axis, what can you tell me about one of these points? Which one is 0? X. So to get the y-intercept, I do what I always do. I let x be 0. And if x is 0, I get negative 3/10. So my y-intercept is negative 3/10. Similarly, how will I find my x-intercept? What can you tell me about that point? Y is 0. So to get an x-intercept, I'm going to let y be 0. So I go back to my equation, and I let y be 0. So 0 equals 2x minus 3 over 5x plus 10. How would I go about solving that? Multiply by 5x plus 10. And what's going to happen since that's a 0? Doesn't it still stay 0? So it looks like x will equal 3/2. So my my x-intercept is at the point 3/2, comma 0. Now I'm going to connect these dots and try to come up with a shape. Anybody have any idea what's going on here, at least in this section of the graph? Any idea? Based on what we looked at yesterday on our calculators?
Is it a hyperbola?
Yeah. So these look like this, and I know that because these two dots are connected, and these are the asymptotes, so that the curve is kind of like framed by the asymptotes. What about over here? What do you think is happening over here? The same thing, but up here. Now, I am comfortable with that. I think Jessica's comfortable with that. If you're not comfortable with it, then plot some more points. Plot some more points till you see what's actually going on. This is a picture of that, though. We're going to do another one here real quick. Now that we're all here, we can do another one. These are the ideas our focus is on today. So we're starting by doing a little graphing without the calculator of some basic rational functions. You are responsible for knowing how to find all the asymptotes, holes, and intercepts. We'll talk about max and min in a minute. Okay, so let's do another picture. Let's do another equation. Fill in this information. All right, here we go. Let's do this one. Okay, let's graph this one. Any idea where to even begin?
Factor.
Yeah, definitely I would factor. Okay, so the numerator is the difference of squares, and the denominator factors like that. All right, what do you notice? Oh, you can cancel. Okay, now why is that a big deal? That's a big deal because what does that tell me I have? A hole in my picture. I have a removable discontinuity. If you look at this, before I cross these out, if you just look at this big, huge problem, you would say to me, whoops, oops, oops, think about domain. We got a problem. X can't be 3, X can't be 1, right? But when I look at this problem, after I cancel, could now X be 3? It can, can't it? It can't be 1. It still can't be 1, but it could be 3. And in fact, if it were 3, if I did plug 3 into this, and why am I picking 3? Because that's the thing I canceled out. That's the thing that didn't used to be allowed, but now it's allowed. So I'm putting 3 in. What do I get? What does this equal if I put in 3? 6 over 2, which is 3. Now what does that mean? How do I illustrate that graphically? What's happening at 3 comma 3? It's going to be an open circle. It's going to be a hole. I have a hole at the point 3 comma 3. Now why do I have a hole at 3 comma 3? Listen, pay attention. I have a hole there because in the original problem, x couldn't be 3. But once I canceled, now x can be 3. So I plugged 3 in, happened to get 3 out, so I have a hole at the point 3 comma 3. Now, let's go back to this. In the beginning, x couldn't be 3 or 1. Can x be 1 now? No, x still can't be 1. So how does that get graphed? Vertical asymptote. Now, I need a horizontal asymptote. My vertical asymptote is x equals 1. Why is my vertical asymptote x equal 1? Because x can't equal 1. You cannot put 1 into this problem. Because we talked about it yesterday, it's a domain issue, isn't it? Can't have a 0 in the bottom. Now what about a horizontal asymptote? Juniors, you were here before. How did we say we were going to find those horizontal asymptotes? The coefficients on the whatever the biggest power is. So the biggest power in this problem is x squared. What coefficient do I have here? 1. What coefficient do I have here? So 1 over 1 would be my asymptote. Y equals 1 is my horizontal asymptote. Remember, the asymptotes are the lines that kind of shape the curve. Okay, now I need my intercepts. What are the intercepts? Those are the points where we cross the axes. And how do we say we were going to find them? They're points. What do we know about each of these points? They have a 0. For the y-intercept, x is 0. For the x-intercept, y is 0. So if I plug 0 in for x, and you can do it here or in your reduced problem, it's whatever's easiest for you. Won't matter, you'll get the same answer. Might as well do it here. If I plug 0 in, I get what? If I plug in negative 3, or no. If I plug in 0, I get negative 3, right? Now remember, I lost it all on, but that's y equals x plus 3 over x minus 1. So if I put a 0 in there for the y, what's that going to give me? Solve that. What am I going to get for x? If I'm going to get negative 3. Very, very good. She got negative 3 because she multiplied this over to here. It stayed 0. So x has to be negative 3. Good. Now look, you've got these 2 points right here. Do you have a feeling for what this thing looks like? Do you have a feeling for that? What do you think's happening over here? Same thing. I heard somebody say it. Same thing. Don't forget you got a hole there, though. You got to kind of skip over that, and that's your picture. Now again, I have this huge advantage that I've graphed hundreds of these things in my life, so I'm perfectly comfortable with connecting those dots. If you aren't, what can you always do? Plot more points. Always you can plot more points. So if you feel like, gosh, I really don't know what this looks like, then go ahead and put a few more points into your equation and plot them. All right, I've got some practice, old quizzes and things with more on this, but we need to continue on with the discussion. We can practice some more of these maybe tomorrow, but we've got some other things we need to look at. Last night, actually, in your homework, I don't know if you had a chance to look at it or not, but there were a couple questions about maximum and minimum. And I don't think we need to necessarily spend a lot of time on that. Once I tell you, if you didn't already figure it out, To find the maximum and minimum, well, first of all, let's make sure we know what I'm talking about. Let's say I put a curve into my calculator, and right now we're going to be doing this totally on the calculator. We're going to find maxes and mins on our calculator. So let's say I put in my equation, y equals, type it in, I get this picture. Does everybody understand this point right here would be considered a relative minimum? This is called a relative minimum. Does that make sense to you? Do you know why that point is a relative minimum? Because it's the bottom of a valley, right? It is not the absolute minimum. Why? Why is that point not the absolute minimum? See this right here? What's he doing? He's going down, 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 down forever, right? So these points are going to be lower than that one, but this is called a relative minimum. To find a relative minimum on your calculator, you do exactly what you do when you find a zero. When you go to second calc, there's a whole list of stuff there. One of them is zero, but another one is minimum. Once you press minimum, it's going to ask you for left bound, right bound, and guess. So it's going to work exactly like the zero button. So you'll graph this thing, you'll press second calc, choose minimum, and then do left bound, right bound, guess, and you'll get that point. Same thing for a relative maximum. Only obviously when you do second calc, you'll choose the maximum option. Okay, those are pretty simple. Give that a shot when you get a chance and see what you come up with. That's exactly what you did when you found the zeros. Now, symmetry is a little bit more involved. The idea of symmetry is pretty easy. Can anybody describe symmetry in your own words? What are we talking about when we say symmetry? Well, let me give you an example here. This equation looks like this when I graph it. And it is said to have symmetry about the y-axis. That means that if I folded my paper on the y-axis, if I could somehow fold my board here, what would happen to these two pieces of the curve? They'd be right on top of each other, right? They're mirror images of each other. That's what symmetry means. If this is an axis of symmetry, then the left side mirrors the right side of that line. Now, some curves have symmetry about the y-axis. Some curves have symmetry about the x-axis. Would you agree that appears to have symmetry about the x-axis? They can have symmetry about the origin. So something like this would have symmetry about the origin, because if you took this and flipped it across the origin, this is the shape that you would get. And some things have symmetry about the identity line, the line y equals x. So an example of that might be this line right here. This line has symmetry about the line y equals x. So what we are going to learn how to do today, or maybe review if you already know how, we're going to take an equation and we're going to determine which special symmetry it has. And the special symmetries are y-axis, x-axis, origin, and identity line. So here we go. These are the tests of symmetry. I'll just take an equation. All right, so we'll see what happens here. We're going to test for symmetry about the x-axis, the y-axis, the origin, and the identity line. Now, the tests are the same from problem to problem to problem, but it'll look different because we're using this particular equation. So here's the test of symmetry for the x-axis. Change, let's say this, let's just do this. make all y's negative. Because if we are symmetric about the x-axis, that means we're going this way. So positive y is going to become a negative y when you fold it across. So here's what that looks like. Negative y equals 2x squared plus 3. Now ask yourself, is this equation, if I make all the y's negative, will this equation that I end up with match exactly the equation that I started with? No. So this one is a no. There is no symmetry about the x-axis. An example of an equation that would have symmetry about the x-axis. What about x equals y squared? If I made the y's negative, would that equation simplify to be the same as this? So this one would have symmetry about the x-axis. This one does not. So quick recap, what's our test of symmetry about the x-axis? Change the sign on y, make y negative. All right, how about x-axis? You want to take a wild guess? If the test of symmetry for the x-axis is to make the y's negative, what do you think the test of symmetry for the y-axis is? That's right, make the x's negative. So what would this equation look like if I did that? Y equals 2 times negative x squared plus 3. Now you need to simplify that. But if you do simplify it, if you do simplify this, will you end up with this? So this one has symmetry about the y-axis. New vocabulary word. If a curve has symmetry about the y-axis, it is referred to as an even function. An even function is a function that has symmetry about the y-axis. And what that means is you can change the sign on x without altering the curve. So if you put in a 6, you're going to get the same output as if you put in a negative 6. Origin. Anybody want to take a wild guess? Now let's just look at what's going on here. When we've tested for symmetry about the x-axis, we changed the sign on y because we were going this way. When we did the x-axis, or the y-axis, I mean, we changed the sign on x because we were going this way. What do you think about the origin? What do you think we're going to do to test for symmetry about the origin? Both. Very good. So we're going to make all x's and y's negative. So what would that look like in this equation? Negative y equals 2 times negative x squared plus 3. Are the gnats bothering you guys? I saw somebody go like this. They're awful down here. I think the recycling bin out there has gnats in it or something. I don't know. They're just swarming. All right, simplify it. If I simplify that, does it boil down to exactly what I started with? No. An example of one that would. How about something as simple as this? Y equals x. If you change the sign on both and simplify, will it simplify back to the original? Yeah. So that's an example of one that does have symmetry to the origin. And finally, I kind of lost it up here, but we're testing for symmetry about the identity line. This one is the tricky one. Anybody guess or remember how to test for symmetry about the identity line? It's real easy. You switch your variables. So our new equation would be x equals 2y squared plus 3. Now, is that that the same as the equation I started with? No, obviously not. You're thinking, well, Mrs. Ford, are there things that have symmetry about the identity line? Think about your circle equation. What would happen if you switch the variables in that equation? Wouldn't it be the same? So that one has symmetry. It's not a function, but it has symmetry about the identity line. So there are functions out there that have that symmetry. All right, so recap. How do we test for symmetry about the x-axis? Make all the y's negative. How do we do the y-axis? Make all the x's negative. How do we do the origin? Make them both negative. How do we do the identity line? Switch your variables. Okay, so we're okay with that. All right, next, increasing, decreasing, and bounded. You have run into those words in other exercises. I mean, even, in chapter P, we were running into those words. Now we have to formalize it a little bit, not a ton. I don't want this to become hard or yicky for you at all. But let me just draw a graph up here, just some random picture. This is not anything special at all. This is just some random picture. I want to talk about increasing and decreasing. This is easy. Increasing means, where does the curve go? Up. We draw from left to right. So as I'm moving from left to right, if I were tracing this picture, where would my pencil be going up? Those are called intervals where the curve is increasing. So would you say that I'm increasing on this part of the curve? So that interval is from -2 to -1. From -2 to -1, these are x values now. From -2 to -1, my pencil is going up. Is there any other part of the curve where my pencil is going up? Yes, I guess I better plot that a little more carefully. From here to here, my pencil is going up, right? So another increasing interval would be from 2 to 3. So when the question says, on what intervals is the curve increasing, that just means look at the x values and where's your pencil going up. Now similarly, where are the decreasing intervals? The decreasing intervals would be from -1 to +1. Would you agree with that? And that's it, isn't it? Now what about this interval from 1 to 2? What's going on there? It's neither increasing nor decreasing, right? So these are the increasing intervals. There's only one decreasing interval, and that's all there is to it. This curve is bounded. It is entirely, there's a ceiling and a floor on it. That means it's bounded. What's the upper bound? Where's the ceiling on this? 2? What's the lower bound? Where's the floor on this? -2? So this curve is entirely contained between -2 and 2. It is considered bounded. It is bounded above by 2, below by -2. It is bounded. As opposed to your classic exponential curve, which we'll study starting tomorrow, your classic exponential here, would you say it is bounded below? Be careful. Does it have a floor? Mm-hmm. It doesn't touch its floor, but it's not going to go below this. This is an asymptote. So this is bounded below by 0. It's not going to go lower than 0. Is it bounded above? No. Do you see that? no ceiling. Therefore, this curve can't be called bounded. This one is called bounded because it has a floor and a ceiling. This one is not bounded because it doesn't have a ceiling. It is bounded below. We use that vocabulary. It's bounded below, but it's not bounded. Bounded, that word, means contained, like in a box. This is not contained. Look at one more. Make sure we have that vocabulary straight. How about, how about this? Bounded below? Nope. Bounded above? By what? 0. Highest it goes is 0. So it's bounded above, not bounded below. So if the question were, is it bounded, you would have to say no. To be bounded, you have to be bounded below and above. Okay? All right, let me take attendance real quick, and then let's do a couple practice things. Got some old quizzes. I didn't run them off, but we can do them. I got Maria, do I have Anna? I got Brandon and Maggie. Carter, do you have Carter? Anna, Julia, Katie. I got Katie, right, yeah. Nick, Newman. I got Alex, Delaney, Reed, no Reed. Got Harry, Janelle, Andrew, Gianna, Manuel, Stuart, Logan, Stark. Stark, Strife, Swan, Emma Bealey, Gracie, Jessica, Kelsey, and Michael. Good deal. Okay. All right, so let's try a problem now. Of all these, which kind would you like to practice? Oh, you don't care? Okay. No one cares about any of that? Okay, well, I will. Oh, by the way, forgot another vocabulary word. What did I tell you even meant? Symmetric about the y-axis. So even is y-axis. Even means a function has symmetry about the y-axis. Okay? Odd, and this is the easy one to remember, odd means origin symmetry. And you remember that because origin and odd both start with O. So if someone says to you, is y equals 3x odd, and I'm going to make this, I don't want you to think anything with 3, so I'm going to make that a 4. Is y equals 4x odd? To answer that question, you would do the test of symmetry for the origin. And what is that test? Make both negative. So if I did that, if I made my y negative and my x negative, and then simplified, do I end up with the original equation? So the answer to the question is yes, it is odd. It has symmetry about the origin, so therefore this is considered an odd function. Emma?
What's the example of one where someone works
If I put a 1 on the end of this equation, then it isn't odd anymore. Because as soon as I put a 1 on the end of it, when I divide out this negative, this becomes a -1, and now it is not the same as the original equation. You put the negative on, you actually make x negative, and you make y negative. It's not like both sides of the equation. It's the individual y and the individual x that get made negative, yes. Okay, so vocabulary, even means symmetric about the y-axis, odd means symmetric about the origin. Good.
So there are, like, examples where it would be odd or even, like.
Oh yeah, here's an example. This, most things aren't odd or even.
Uh,
Most random curves don't have symmetry about stuff like the y-axis and stuff. Okay, yeah, definitely possible. Now, some things, not necessarily functions, but some things might have symmetry about both. For example, Michael, think of your circle centered at the origin. It would have symmetry about both the y-axis and the origin. So in that regard, it can be considered even and odd. And it's not a function though, so we gotta keep that in mind. All right, let's do a quick review here of, okay, I want to talk about asymptotes. Vertical and horizontal. Now, juniors, I'm going to rely on you because you were here for both examples. The seniors were only here for one example. I want my vertical and horizontal asymptotes. First of all, I'm just going to go out on a limb here and say this problem has no holes. Am I right? How do I know? Nothing cancels. I'm not going to be able to factor and cancel, so there are no holes. But there are asymptotes. Anybody, any junior or senior, I don't care. Anybody have a thought on vertical or horizontal? Gracie?
Is vertical negative 2/5?
You are exactly right. And make sure you give me a letter there, Gracie. X equals negative 2/5. That is my vertical asymptote. And how does she know that? Can somebody put it in your own words? How does she know that? She's absolutely right. Michael?
It's the zero of the denominator.
Exactly. The denominator cannot ever be 0. If you walk out of this room today knowing nothing else, please know the denominator can never be 0. So, what number would make this 0? Negative 2/5. So if I were drawing this, I would have a vertical asymptote at negative 2/5. Horizontal. It's going to be a y equals now because it's horizontal. Where's my horizontal asymptote? Deanna?
3/5.
3/5. Deanna is exactly right. Our horizontal asymptote comes from comparing the coefficients on the highest power. So in this case, all we have is a plain x. So we have 3x over 5x. So I have a horizontal asymptote at y equals 3/5. Harry, can I give you a challenge problem, Harry?
I mean, you can.
Okay. Let's take a look at this one. Now, I think the vertical asymptotes are easy. And notice I use the word plural. I use the plural form, vertical asymptotes. Kind of giving it away. Where do vertical asymptotes come from? Where did Gracie get this again? What part of the fraction do we look at to get vertical asymptotes?
The denominator.
The denominator. So what would make my denominator 0 here, Harry?
I mean, don't you have to factor that?
Okay, so how would that factor?
X minus 2, x plus 2.
Perfect.
And then, would it be 2 and negative 2?
It would be. Make sure you attach a letter, so your asymptotes are x equals 2, x equals negative 2. Perfect, okay? Now that was the easy part, Harry. Now we're gonna do the tricky part. What are the horizontal, or what is the horizontal asymptote? Your curve's only gonna have one horizontal asymptote. What is the horizontal asymptote? Now, you were not here when we did our first example, so you've really not seen too much of this, but Deanna was exactly right. She said to get your horizontal asymptote, you're gonna look at your x's in this case, and just take the coefficients, 3 over 5. Now, what's different about your problem here? What makes it a challenge problem?
There's 2 coefficients on the bottom.
Well,
Or just 2?
it's kind of, the idea is, this is a plain x,
Yeah.
and this is an x squared.
Yeah.
Okay, any idea how to handle that?
No.
It's an unfair question, so that's okay, say no, it's all right. Anybody have any ideas how to handle it? Michael?
Well, is it one, because it's the coefficient of the largest power?
Okay,
or-
you are so close.
But
You
do
look at the
Do you
highest
have to
power.
subtract or something like that?
What's the highest power in this problem?
2.
X squared.
Okay,
How many
yeah.
x squareds are on the bottom?
1.
1. How many x squareds are on the top?
Zero.
So I have 0 x squareds on the top. I must, you're right, Michael, you must look at the highest power. So I look at the absolute highest power and I compare those coefficients. So what happens?
Just 0.
It's just 0. So this horizontal asymptote is at 0. So we look at the highest powers, and if it happens to be missing, we put it in. We put it in. Very good. Thank you, Harry, for being such a good sport about that. That was not a fair question. Okay, next. Let me see, trying to find a question. Let's see. How about, this will be your classic sine curve. We'll learn about this a little bit later. Is this bounded? What would be your answer to that question? Is it bounded? Yes. And why do you say it's bounded? Because it has a ceiling and a floor, right? It's entirely contained. This label is actually -1 and this label is 1. So you would say it's entirely contained between -1 and 1. It is bounded. How about this one? This is a tangent curve. This was a sine curve. This is a tangent curve. Would you say the tangent curve is bounded? No, not below or above. It goes on forever and ever. Okay. I think that's it. Have a wonderful day. Hey, listen, tomorrow's the deadline for math. There's a bunch if you haven't signed up yet. If you have your money, let's get it taken care of right now.